So Jean-François asked me to give this seminar, and I would like to thank him for that. He also told me that the seminars will be in English, so I'll be sticking to English. What I would like to tell you about today is to show you that in active matter, many questions are completely open. It's a non-equilibrium system. These are non-equilibrium systems for which, in general, okay, I'll give 2 minutes to everyone to come in. So what I'd like to show you is that even though active matter comprises non-equilibrium systems for which we don't have any thought of general theory, there are still some aspects of the field in which we have made lots of theoretical progress over the past 10 years, and which allow us to both predict and use, predict collective behaviors and use external cues to control them. So I thought Jean-François would be giving a broad introduction to active matter, and I decided to give a very focused one, but it turned out that actually we chose the same angle to introduce active matter, which is to speak about fluctuation dissipation theorem. So I'd like to contrast what I will call an active system with what typically we call passive ones. So the standard passive particles you can consider is a colloidal particle, a particle which is small enough that thermal fluctuations are important, embedded in the fluid. So here you have an image of a silica bead in the surrounding fluid, and you may imagine that this particle is moving at a velocity v, and you want to describe its dynamics. So the standard model you'd use for these passive particles is a Langevin equation. So it's just Newton's third law, so you have the mass times the acceleration, which would be equal to the sum of the force. And if you look at the forces, here I've written 3 of them. The first one is an external potential. It could be gravity. It could be one of these optical tweezers that Jean-François was talking about. And then you have 2 others, which actually are just the 2 faces of the same forces. So if you look at this particle, it's embedded in a fluid. And so you have a lot, typically 10 to the 8 molecules of the solvent, which are interacting with the bead. Now, if I wait a few seconds, the fluid molecules will have moved around, and the forces they will exert on the particle will not be the same. If I look at the average force that the fluid molecule exerts on the particle, and I can compute it, and what I get is what we call the drag, minus gamma v. And that tells you that on average, the fluid molecules exert a force on the particle which opposes motion. And this is a dissipative force in the sense that if you look at the power injected in the particle through this force, it's negative. So it's taking energy out of the colloid. And of course, because that's only the mean force, around this average behavior, you have fluctuations. And these fluctuations is typically what we represent by Gaussian white noise. And if you look at the impact of this force, on average, it ejects energy in the system. And this system is if the surrounding fluid is in thermal equilibrium, what you can show is that the dissipation and the injection of energy, they're related. They're related to an application of the fluctuation dissipation theorem that Jean-François told you about. And you can see that the variance of the noise here and the prefactor of the drag force are related. The ratio is kT. And that characterizes an active system. So the dissipation of energy and the injection of energy, because they come from the same source, which is an equilibrated fluid, equilibrium is contagious, and the dynamics of this guy will drive it towards equilibrium. Now, if I consider an active particle, for instance, a bacterium, Escherichia coli, of course, the same 2 forces will also be present. If the bacterium is moving at speed v, there will be a drag force that will typically be minus gamma v. It won't be exactly the same gamma, but it will be the same idea. And of course, there will be fluctuations around this force, and so you also have injection of energy into the bacterium motion from the fluid. But that's not the main source of activity. The reason why the bacteria is moving is because using its flagellum, it's pushing on the fluid. So there is a reaction under the fluid. And there is a force which is pushing forward, which I will call FP, a self-propulsive force, whose orientation will be along the body axis of the bacterium. And so here what you see is that you still have the same source of dissipation, but now you have 2 sources of energy. And the result is that you don't have a fluctuation dissipation because the main source of energy is the internal one. It's completely disconnected from the external one. And you have much more freedom than for passive particles because you have not constrained, you have less constrained injection of energy. So if you look in the literature at typical models of active particles, they always look like variations around it. Typically, inertia is negligible, so you will have a 0 here. And often, you don't write separately the thermal noise and the activity. You just add one noise eta tilde. And the reason why you would say that this guy is active is if this noise, or when this noise, does not satisfy a fluctuation dissipation with respect to this friction. So that's to give you a microscopic definition, particle-based definition of what an active particle is. Now, why is it interesting? It's interesting because these consumption of energy from an internal sources give a mechanical drive at the microscopic level. So each individual particle of your active medium will be driven out of equilibrium. That releases the constraints that equilibrium physics gives you, and you have a much richer phenomenology. So you can have the collective motion of fish shoals. People have done dense motility assays of microtubule filaments, which make a kind of local nematic order, but with tons of defects, which in addition are motile, which is something that we don't see in equilibrium. And you also have Denis Barthelot will come next week and speak about the propagation of colloidal flux. So again, this time it's a synthetic particles made of lots of small beads that are traveling together, something that would be impossible in equilibrium. So the main interest, the main reason why people have been working a lot on active matter is this new dynamical phenomenology. The fact that it's biologically relevant, it's almost a signature of being alive, being active. And also the fact that now people start to be able to engineer active systems. And so soft matter has been a huge revolution in the 20th century. That's what allowed us to have LCD screens. And of course, the possibility of having active soft material is something that interests a lot of people. So having gotten rid of the constraints of equilibrium physics is good because you get new phenomenology. But it's also really bad because by stepping out of equilibrium, we've lost our guiding principles. And that's what we're looking after. So what do I mean by that? If you open a modern textbook on equilibrium statistical mechanics, typically people will put forward three main properties. The first one is that in steady state, you have time reversal symmetry. That's typically what I put forward when I give talks, which are not the talk I'm giving today. Another one is that, and that's really something which is unique to statistical mechanics in physics, that we can replace dynamics and simply look at the static properties of systems. If you think about Schrödinger equation, Maxwell equation, Navier-Stokes, all these equations are dynamicals. When you do stat-mech, you do ensembles, equilibrium stat-mech. And that's what I would like to focus on today, because we don't only replace dynamics by a static approach that we could do for anything which has a steady state, but we know what ensemble to use. And we know that the probability of observing a given configuration in steady state is given by the Boltzmann weight. So why is this useful? Imagine you want to understand liquid-gas phase separation. So you take a fluid, it can be either a molecular fluid or a colloidal one. And so you can say passive volume particles which interact with attractive interactions. Now, you know that the steady state will be described by Boltzmann weight. So if you ask yourself, what is the typical energy I will observe in my system? What's the typical configuration I will observe? You know that what you have to do is to make a competition between entropy and energy. And the relative strengths of the two will be controlled by temperature. Entropy will tell you that you want to minimize the information you have on the configuration. So you want to maximize disorder that promotes a gaseous phase. While if you have attractive interactions, the energy will favor cohesion. So because the ratio between the two will be controlled by temperature, you know that at high temperature, entropy will win. You'll see a gas. And as you lower the temperature, the energy will win. You'll get a phase transition. And you'll go from a gas state with a liquid, and maybe with coexistence if you're in the canonical ensemble. Now, outside equilibrium, you don't have any generic formula for the steady state. Sometimes it exists, but you don't know what it is. And so if I ask you, design me an out-of-equilibrium material that would do a liquid-gas phase separation, you don't know what to do. Because you don't know, for a given temperature, what are the guiding principles, what will select the steady state you have. Maybe attractive interactions is a good idea, maybe it's not. And that means that if you want to go towards these soft-active materials, you don't have guiding principles. Now, there is one area in which I'd say there is an exception, and that's motility control. And over the past 10 to 15 years, what people have done studying active particles has taught us few guiding principles, which I'd like to present today. So I'll be discussing two types. So everything in my talk will be starting from microscopic and going to emerging behaviors. And I'd like to give you the two typical type of trajectories I will consider. So we'll consider particles which are self-propelled. And what that means by that is that they have this constant self-propulsion force. I'm looking at overdamped system. So in practice, they have a fixed, they have a self-propelling speed v here. And they can have different type of isotropic reorientation mechanism. If you're studying bacteria, like Escherichia coli, a typical dynamics is what we call a run and tumble dynamics. So the particle goes in straight line, and at a constant rate, fully randomize its orientation. Go in straight line, fully randomize its orientation. And so typical dynamics would look like that. Another type of particles, which describe better the type of rolling colloids that Denis Barthelot will be speaking about next week, is self-propelled particles whose orientation undergo rotational diffusion. So instead of having instantaneous randomization of the velocity, you have a slow redirection. So you have a random walk which is persistent. And what I would like to show you today is that if you know what you know about the statistics of the velocity, can allow you to infer statistics of the steady state and how the properties of V can control the steady states. I'll be going briefly through 4 different parts. The first one will not really be self-organization, it will be driven organization. And what I will show you is that if your swim speed, your self-propulsion speed is not uniform in space, then your steady state will not be uniform and you can control, and you know what it is. Then I will be moving to interacting systems, and I will be discussing what people call quorum sensing interactions, which is a type of interactions in which your velocity depends on the local density. Imagine you're running in the subway to catch a train. If there are lots of people around you, you run slowly. If there are nobody, you can run fast. That's this type of interactions. And then I'll discuss applications of these guys to bacterial pattern formation for both single strain and multi-strain systems. Okay, and again, as Jean-François, feel free to interrupt me whenever I say something that's not clear. Okay, so imagine that you have an active particle with a self-propulsion speed, v, that depends on position in space, r. I want to write down a master equation for the probability density, and in here I'm working in 2D, of finding a particle at position r going in a direction theta. So theta will be the angle, say, with the horizontal, the body axis of the bacteria or the particle is doing. So typically what I will have is that the time derivative of p is minus the divergence of a current, and this probability current is simply the advection of the probability by the self-propulsion of the active particle. And then you have a second term, theta p here, which I won't detail in general. It's just what controls the randomization of orientation. So if you have rotational diffusion, meaning that the body axis of the bacterium is doing rotational diffusion, typically you just have a Laplacian, a second derivative with respect to theta of p. And if you're on a sphere, that would be just the angular part of the Laplacian. If you had run and tumble particle that hops, that change direction at rate alpha, you'd have a loss term that would be minus alpha p. That's the rate at which you go out of direction theta. And then you have a gain term, which is alpha over 2 pi, integrated over theta prime, p of r theta prime, and that corresponds to the flux that you have from people who are at the good position r, in the wrong direction theta prime, and that hop into the correct direction at a rate alpha d theta prime over 2 pi. Now, why am I writing this? Because if I now go back to my initial problem, and I want to compute a steady state of this guy, it's very simple. First, because the randomization of orientation is isotropic, if I try for p any function, which is just a function of position, but not a function of angle, theta p will be equal to 0. That's simple to see in this case. You have a Laplacian acting on theta. There is no theta here. That gives you 0. Now, if I go back to this equation, I put a 0 here, a 0 there. So I just did the divergence of this guy to be 0. And I see that if v times p does not depend on r, well, v times p will be a constant. Divergence will give me 0. And what this tells me is that the steady state probability of this system is simply that p of r is 1 over v of r. So this is something very intuitive. It's just telling you that if you look at something which is self-propelled, if you go fast somewhere in space, the probability of finding you there is much smaller than in regions in which you go slower, because you spend most of the time where you go slower. So there is something very intuitive. One thing, so that's something that Schnitzer had realized for run-and-table bacteria that can be generalized to all types of active particles. Here you may have noticed that I don't have any translational diffusion, so I don't have a Laplacian on R. You can add it. It only changes qualitatively this result. So the steady state is now 1 over square root of your diffusion constant plus v squared times tau, where tau is the persistence time of your dynamics. But basically, this guy scales as 1 over v. So you spend more time where you go slower. Now, that's, of course, a result you derive from a simple, yes?
Is it possible to normalize the probability?
Yeah, you just put a constant on top. This is a linear equation. So if you multiply by any constant, you normalize the probability. And okay, I see your point. So if you want it to converge to a steady state, you would need to select a v of r that confines your, if that's, yeah. So if, for instance, you have v which is homogeneous in infinite space, you don't have a steady state. If you're in the box, then you're fine. So that's, of course, a result you get for this small model, but you may wonder how relevant it is for, say, bacteria or active particles. Now, it turns out that you can do these experiments with bacteria because there is something called proteorhodopsin, which is the solar panel of bacteria. So it's a protein which, when you shed light on it, can power proton pumps. And so you can have bacteria that you genetically engineer so that their propulsion speed is controlled by light. And so people have checked quantitatively that indeed the density then is proportional to 1 over v. The translational diffusion is completely negligible in this case. And you can do fun things with it. So that's what was done in the lab of Wilson Poon in Edinburgh. This is what was done by Roberto Di Leonardo. So it's not just a crappy picture of the Joconde. What they've done is they have sent a light field that corresponds to the head of the Joconde, and that's the density of bacteria. And it's you could say, well, that's just a steady state. Maybe it's not so interesting, but you can actually play with it. So for instance, you can start with a picture of Einstein, and you change the field of light that you impose, and you get a picture of Darwin instead. Okay, so that's not self-organization, it's externally driven organization. It may still be useful. For instance, what people are doing in Edinburgh is that they are then making the bacteria synthesize silica. And so the things that you've driven with the light, then you kill the bacteria, and the silica has created the pattern. So it's a new way of doing patterns. I don't know how useful it is versus lithography, but at least it's a new type of technology that you can do with bacteria. And then these guys can do many things, synthesize antibiotics and stuff like that. So there are lots of things you could do in this direction. Now I want to switch to what happens when you have experiments. So what I told you here is that if your velocity depends on position, then you accumulate where you go slower. Now, something else that can happen to you is that your velocity doesn't depend on position, but it depends on density. And again, you have this image. If you're trying to run through a crowd, the denser the crowd, the slower you go. Again, in bacteria, you can do synthetic engineering, and you can build that. So this is a cartoon of a bacterium. And you can put 2 plasmids in the bacterium, which are small pieces of DNA that will code for proteins. And the first plasmid here, it creates these molecules here, which are represented in blue, which basically go out of the cell, diffuse in the environment. And they can also bind to some other proteins, which are created by another gene. And when these guys bind together, then this complex will go and regulate some proteins, like for instance, Kisi. Kisi is a protein that's involved in the run and tumble dynamics of bacteria. So basically, if you don't have Kisi, you spend all your time tumbling. So you're just changing direction all the time. You're not going anywhere. You need Kisi to resume a running phase. So if you don't have Kisi, you don't move. If you have lots of Kisi, you move a lot. And so by building this type of genetic circuits, you can engineer systems in which at high density you stop, and at low density you go fast. So these are experimental results. They plot the diffusion constant versus density, and it's normalized to the one without the circuitry. And you see that basically at low density you have something which is flat at 1, and then suddenly above a critical threshold, bloom, it falls sharply. So that's also something you can again put in a small model like the one I study. And here I'll do something very simple. I'll just say, well, my velocity is my self-propulsion speed times the direction in which I'm pointing. And then I'll have whatever dynamics I want. I can have rotational diffusion, tumbling for the orientation. Now, what is this guy? Well, this guy is a representation of the fact that I'm producing signaling molecules that go outside, that diffuse, and that are degraded. The typical lifetime of these AHL molecules is 10 minutes. So typically, you have to imagine that the bacterium, when it's swimming, it feels a concentration signals, which is made by the bacterium within 100 microns around it. So it's basically measuring an effective density with some convolution kernel. So you can take this model, you put it in the computer, and you play with V of rho, which would correspond something like that. So I go fast at low density, and then suddenly I fall down. So if you do that, again, you can do that with non-double particles or with active brilliant particles. And if you make simulations, that's what you see. So here, we've taken a V of rho, which is sharply decaying. So initially, the system is homogeneous. Each of the dots is a particle. They all have a small arrow on them, and the color code is the local density. And what you see is that you have initially a rapid instability that makes lots of dense cluster appears in the dilute region. And as time goes on, you have a coarsening. If you try to characterize this coarsening, it looks a lot like an equilibrium liquid-gas phase separation. And another thing which is interesting is that microscopically, the left and the right system, they have different reorientation dynamics. But you can see that when you zoom out, from a microscopic point of view, it's completely impossible to distinguish the two of them. And you have a form of universality that at this emerging behavior level, the microscopic details of how you randomize your velocity is irrelevant. This coarsening process, in which you have a small droplet that evaporates and whose mass is redistributed on neighboring ones, in equilibrium you also have it. That's called Oswald-Riepening. Okay. So again, this is a simulation in the computer. You may wonder what happens with bacteria. I'll come to that later, but first I want to show you an experiment with colloidal particles, and I will keep on going through the zoo of active particles which exists, which people have synthesized. So what people do is they take, I think it's a latex bead, and that you coat half of it with gold. And you put these colloids in a water-lutein mixture just below the critical temperature. So if basically you heat up a little bit a region of these liquids, you'll have phase separation. Then what people do is they shed light on these colloids, and the part which has gold heat up more than the other one. The result is that the temperature of the fluid close to it increases. You have lutein water decomposition, and you get a gradient of the order parameter that will drive, by diffusiophoresis, the motion of the colloidal bead. So here you have a movie in which you have this big bead surrounded by small ones. I just wanted to show that you don't have attractive interactions between these guys, and which are self-propelled. So I'll play again the movie. So you have two of these guys that collide. You can see that really there is almost no attractive interaction this guy keeps on going together. Now, the second thing that these people can do, so these are very, from an engineering point of view, these are very interesting particles, because with the light, you can control whether they're self-propelled or they are passive. And what people have done in this lab, and that's in this paper, is that instantaneously with a CCD, they measure the position of the particles. They compute the local density around each particle, and they use that to decide what will be the light at the next instant. So in real time, your particles have a velocity that depends on the local density, but from the computer. And the result is that if the velocity is constant, you have something which is homogeneous. While if you use this feedback loop to control the V of rho, you do get this phase separation I was talking about on the previous lab. So in a way, this is just something that tells you that theory is robust to realistic experimental conditions. You could say that this is really a kind of analogic simulation. But I think that's still something very interesting, because if indeed we think about active matter as something we want to engineer, then definitely having handle that allows us to control the collective property is something very important. That's why we like LCD, not because just we have phase transitions, but because we can use them as displays. Okay, so how can we understand the physics of this phase separation? So what I told you at the beginning of the talk is that if you have a non-uniform speed, then you typically accumulate in slow region, so that the density typically wants to relax to 1 over the velocity. Now, what I'm telling you is that I have a velocity that decreases with the local density. So what this will tell me is that I will slow down in dense region. I accumulate in slow region. The slow region are the dense region, so I accumulate in the dense region. That's a feedback loop that will drive an instability. Let's see how it happens. Imagine you have a system which is homogeneous at some density rho naught, given by kappa over v naught. And imagine you have a small fluctuation of density. Because the speed depends on the density, you also have a small fluctuation of the density. So v of rho will become v of rho, and if I linearize v of rho plus delta rho, I get v of rho plus v prime delta rho. Now, I know that the density, it wants to relax to 1 over v. So I've started with this initial condition, but now I want to relax to kappa over this guy. Okay, so kappa over this guy, again, I assume that my fluctuation is small. I can expand. And what I get is that I started from rho naught plus delta rho, and I want to relax to rho naught minus rho naught v prime over v delta rho. So if this guy is larger than that guy, I will have amplified my initial perturbation, and I will have a linear instability. You can look at what is the quantitative criteria that give you that, and you find that if v prime over v is sufficiently negative, then you get a linear instability. That's a hand-waving argument. Turns out that if you do the math, it's also a quantitative argument for the linear instability. And so, of course, then in turn, if you have increased your modulation of density, you will increase the modulation of speed. So that's the initial instability. And one of the things you'd like to understand is where does it lead to? What's the steady state of this guy? So the answer is it leads to something that we've called motility-induced phase separation, but at this level, it's not easy to know that it will be a phase separation. So how do you answer this question? So let me first go through how you answer this question in equilibrium. In equilibrium, if I give you a colloidal model with attractive interaction and I ask you to compute the steady state, you can write Boltzmann weight and you stop there, because we don't know how to compute anything analytically out of that. So what you do instead is you coarse grain your system and you work at what we call the hydrodynamic level. So if you have a system in which the correlation length is very large when compared to the particle size, but you're still far away from criticality, so that noise is not relevant, the large-scale dynamics of your system will be typically given by a hydrodynamic equation. So here, I'm not creating or destroying particles, so my only hydrodynamic mode will be the density, and its dynamics is just a conservation equation. Rho dot is minus the divergence of a current. If I'm in equilibrium, which is not the case for the bacteria, typically the current will be minus a mobility times the gradient of a functional derivative. And this functional derivative, I will typically not compute it, but I will postulate it and I will expand it following Ginzburg and Landau. And that's the type of free energy I would be writing. My free energy would be an integrate through space of a local contribution to the free energy. And then I'll have some coefficients, and I'll have gradient squares, and then I would have higher order gradients. Now, if I want to understand the steady state predicted by this system, what I have to do is I just have to find the profiles, the density profiles that externalize this free energy. So I want to minimize my free energy, and if I'm working in a system which is closed, I know that I have one constraint, which is my total number of particles is fixed. So how do I do that? Well, imagine that you have a phase-separated system, so you have a droplet of liquid surrounded by gas. You look at an interface, you go through an interface, typically the profile looks like that. And what you will want to do is I want, for instance, to compute the gas density and the liquid density. And to do that, I will externalize my free energy with this type of profile. When I do this, what I have to do is what's called a common tangent construction on the local part of the free energy. So I draw f of rho naught versus rho naught. I look for the line which has the same slope and touches the line twice. And I know that the steady state is given by two constraints. First, both phases have the same chemical potential, so they have the same derivative. And they also have the same pressure. And the same pressure means that the intercept here of this line with the vertical axis is minus the pressure, which is given by the minus derivative of the free energy with respect to volume. So that's what you would do in equilibrium. Here, with the active particles, in principle, you're lost, because even if you were able to write down this equation, you wouldn't have this shape. Nevertheless, that's something that we try to do. So you do the coarse graining explicitly for your active particles interacting via quorum sensing. And the dynamic you get is a mass conservation equation. Again, you have a current here, which is given by your mobility times the gradient of something. This something, you can compute analytically its expression. You get a part which is local and a part which has gradient in it. You can compute the coefficients. But unfortunately, these parts here cannot be written as the derivative of free energy with respect to density. So from that, it seems very difficult to infer the coexisting densities. There is a miracle which happens for this system, which is that you can do a change of variable. You can introduce a new variable r of rho, and you take, if you choose r defined as 1 over kappa, where kappa is the coefficient of this guy, then it turns out that the dynamics is not written as the derivative of free energy with respect to rho, but as the derivative of free energy with respect to r, where this free energy has the same form as before. There is a local bit and a gradient bit. But now the local bit is the integral of the local part with respect to r and not with respect to rho. So it's something slightly puzzling. As Jean-François will immediately at the end there, we have absolutely no clue of any physical intuition on that. It's a mathematical mapping which exists. The good thing is that now, if I want to get the steady state of this guy, I just have to externalize h with respect to r. That leads to exactly the same common tangent construction as before, but now on this new function phi of r. I can do that for my model. That allows me to predict in red what should be the coexistence densities for as a function of the ratio between the speed at low density and the speed at large density. So this is the density, that's the ratio. The red line is spherical prediction without any fitting parameter. And the simulation, the dots are the result of simulation. So you see that you have an almost quantitative agreement. So we're very happy when we got that. Actually, I'm not very aware even in equilibrium of many systems in which you can predict without any fitting parameters, the phase diagram of a system. We're still a bit worried by this small difference. So my interpretation of these guys is that to derive this hydrodynamic equation, you do a gradient expansion. I've stopped at the second order in gradient. They should be higher order. In equilibrium, the gradient terms don't matter. Here they should. So if I want to check that this is due to that, I need to find a model in which I can compute that exactly. So of course, I can do that, but what I can do is I can work with mathematicians who know how to do that. And that's what we did in collaboration with Thierry Bodino and Clément Erignoux. And we started from a model I had looked at almost 10 years ago, which is a lattice model. So when you want to solve something exactly, you follow Bernard Herrera and you work on lattice. you put particles on your lattice. You have black particles which hop to the right, white particles which hop to the left, and the particles can tumble. They can change direction. If the hopping rate decreases with the occupancy on the site on which you're hopping, then you get phase separation. So this is 1,000 times 1,000 lattice. There are 6 million particles in these systems, and every time the time hits a decade, the speed of the movie is multiplied by 10. So initially, you don't see much. Then you start to see some granularity. You see light blue regions, which correspond to gas, and you see dense purple region, which correspond to the liquid. And as time goes on, you have a coarsening dynamics. Again, if you use this coarsening dynamics to compute the exponent, you get exactly those of equilibrium liquid-gas phase separation, which is quite remarkable. You'll start to see that either the droplets merge when they touch, or when the distance starts to be big between the droplets, you'll have the Oswald ripening. So this guy will probably evaporate and being redistributed in the guy around. And then at some point, of course, you have power cut in electricity and the simulation stop, which happens before the end of the coarsening. OK, you've understood what's going on. OK, so for these type of lattice models, it turns out that if you choose the hopping rules microscopically wisely, you can construct hydrodynamic equations exactly. So how do you do that? First, you say that at a rate d of order 1, on your lattice, you swap neighboring particle. So that's a rapid process for the one, which has nothing active in it. Then, at a much slower rate, rate 1 over all, the minus particles which hop to the left and the plus particle which hop to the right if the arrival site is empty. So that's the active part of the dynamics. And then at an even slower rate of gamma over L square, a plus particle becomes a minus, or a minus becomes a plus. So I have a bit of symmetric diffusion, much less self-propulsion, and a tiny bit of tumble. If I do that, and I make simulations of these systems, it undergoes motility-induced phase separation if the density is large enough. So here is typically a simulation. That's, I think, a 1D case. And you see that you have a dilute phase that coexists with a dense one. If you compare microscopic simulation with simulation of a macroscopic solution, you get an exact agreement. You have a bit of rounding because of the averaging. But what's interesting is that for these guys, we know how to derive hydrodynamic equations which are exact and which are given by that. They're a bit more complicated than the one I showed you before. Nevertheless, you can still solve them using the same type of change of variables. And here you have the phase diagram, the density versus the self-propulsion strength. Lambda is the self-propulsion strength. And you have this time an exact agreement, which is good news, between the exact solution and the microscopic simulations. OK, so a last model I want to talk about before I go back to bacteria is what happens when you don't put the slowdown by hand. Up to now, I've always looked at models in which the V of rho was there because I had decided that the velocity would go down as the density increases. One thing you can look at is models in which that would be an emerging feature. So imagine that you're running in the subway to catch a train, but you don't see people. You just close your eyes. You just bump in people. So you're interacting with other people with pairwise, purely repulsive forces. People don't grab on you. They just push you back. Now, if you look at the component of your velocity along the direction in which you're going, clearly, all the impact that you have from people in front of you, they slow you down. And most of the time, you bump into people that are in front of you and not behind you. So on average, repulsive forces will slow you down. And for sure, if you do simulations of microscopic particles which are self-propelled and interact with purely repulsive forces, you see motility-induced phase separation. And there we can go back to what I was telling you at the beginning, that if I ask you to guess what type of interactions you would have chosen to create a liquid-gas phase separation active particles, you would have said attractive forces, but strong enough that they overcome self-propulsion, really strong. And what this tells you is that actually it's much simpler to just use hardcore, because repulsive forces will be sufficient, and you'll get phase separation. And I don't think that this is something that's easy to guess. OK, now I want to go back to my bacteria and tell you what happened in this system, which is a bit more interesting than the motility-induced phase separation. It's motility-induced pattern formation. So I have this synthetic biologist collaborator, Jen Dong Huang, in Hong Kong University, who has engineered these bacteria. They do exactly what we want. So their motility decreases at high density. Then they do the magic experiment. They put a droplet in the center of a Petri dish box. They wait 24 hours, and this is what they see. So you have a spreading of the colony. Clearly, the density is not homogeneous, but clearly you don't have phase separation. You get nice patterns, nice circular patterns with rings of fixed sites. So that's very nice. Something's happening, but not what I expected. So what am I missing? So these experiments, first, they don't start from the homogeneous setting, which I described before. They start from a central inoculum, and they take time over 28 generation time. So typically, the bacteria will divide every 20, 30 minutes. So here, definitely, in these experiments, if you want to go from there to there, you have to create matter. And the fact that you have a non-conserved dynamics becomes important. Can I try to account for it? I can try to start from my Hydrodynamic equation describing motility-induced phase separation. And I simply add birth and death. And how do I do that? I open any mathematical biology books, which tells me that birth and death of bacteria is simply given by this logistic equation. Then I speak with biologists who tells me that this is complete nonsense, but that's another problem. And I do simulation of this guy. And what I get is exactly what you see in the experiments. You start from a central inoculum, and as time goes on, you have the formation of concentric rings. So you have a qualitative agreement with the experiments. And the question is, what happens to phase separation? Now, what happens to phase separation is that it wants to generate a region of low density and region of high density. But the birth and death wants to oppose that, because if you have a region of low density, you'll have lots of food, so you can divide, and you can create matter. If you have a region of high density, then you starve out and you die. And so the competition between this guy that promotes phase separation and this guy that would promote a homogeneous system at density rho naught give you microphase separation instead of phase separation. So if you make a simulation starting from a homogeneous system, what you see is that you have formation of dots, but that these dots, they do not coarsen. And as time goes on here, you will have rearrangement. So it's not a bug, it's a feature, because from the point of view of the bacterium, phase separation is probably not something which is very beneficial, but the fact of being able to aggregate in colonies of given size and regulating this size is clearly something which is interesting. So a natural question to ask is, how is this size regulated? And that you can do explicitly the balance of the two phenomena I've been speaking about. Imagine you have a gas bubble surrounded by a liquid phase of typical size R. Okay, that should have been the radius, but that's fine. So motility-induced phase separation promotes phase separation. So there is a flux from the gas to the liquid that would drive the coarsening. And so if I look at the mass in my gas droplet because of this flux, typically it's going down. And the scaling of this decrease is typically the circumference. So if R was a radius and not a diameter, that would be 2 pi R times this typical flux. Now, I also have the burst and death dynamics. And if it's the gas, it's a low density region. So I'm creating bacteria everywhere. And this time, because it's everywhere, the burst rate, the contribution to the mass, is proportional to the area, which is pi R squared. So you see that if I want now to go in the steady state and put this equal to 0, I have to balance this guy with that guy. And I select a radius by balancing these two mechanisms. OK, so that's what happens when you have a single type of bacterium. But now, in nature, it's quite rarely you find isolated bacteria. Typically, they exist in complex ecosystems. And one of the things that you can ask is, now, if you have a mixture of bacteria, can you use this motility control not to self-organize yourself in space, but to mutually self-organize? So we asked Jen Dong Huang if he could take two strains, A and B, and implement a reciprocal motility control. And of course, he said yes. So how does he do that? Well, he played the same game twice. Now I have my red bacteria on the left, which I will call red because it will be expressing M cherry, so it will look red on the pictures. It's producing these molecules, which look red because I've drawn them in red, but of course they're not red. They diffuse in the environment, and now they will go and regulate the motility of the other strain, the strain B. So they will bind with some molecule in the bacterium B and regulate the strength of this guy. Conversely, the activator B here will be creating some molecules in green that will diffuse and will go and regulate the red bacterium. So here, something fundamentally different from the previous case is that bacterium don't self-regulate themselves. If this guy is alone, nothing is happening. In addition, you have lots of things which are proper characteristics of mixtures, like mixing entropies and stuff like that, which makes the prediction of the collective behavior of this guy much harder to do. But again, one thing I should say is that in these experiments, what's regulated is key Z. Key Z controls the rates from tumble to run, not the swim speed as before. So you get density-dependent tumbling rates, but you can redo everything I've said before, and you should get motility-induced phase separation and everything. Again, you do the experiments. Now, measuring is a bit more complicated. That's Yangfeng Zhao, who built the setup. So you have basically 2 light channels that take pictures of red and green bacteria. It's China. When you eat in a restaurant, you have this table on which food rotates. You can do the same with Petri dish and bacteria, so you can have large statistics. And this is what you see. So if you have mutual activation of motility, something that wouldn't do anything interesting in the single species case, you get pattern formation. And when you overlap the pattern of the 2 strains, you see that you have red, green, red, green, red, green. So the species do rings, and they mix. If, on the other hand, you have inhibition of motility, so people who don't like each other, I slow you down, you slow me down, well, you should see if the contrast was better are rings, red and green rings, and this time the rings are colocalized. Just to show you how it looks like dynamically. So that's the green channel, the red channel, and the superimposition of the 2. And well, what you can see, I think we freeze at the movie at the end. So you have the formation of these rings, and you see that where you have a dense red ring, you have nothing on the right. So you have, are you going again? Yes. So you have green ring, red ring, green ring, red ring, green ring, red ring. And you can do the same with the... And of course, can you account for that analytically? Yes, again. This time you have to take n populations of active particles interacting via quorum sensing. And then you ask Agnese Curatolo to construct exactly the hydrodynamic description, which you can do. And you can show that if you have mutual inhibition of the motility, you get a phase separation with colocalization. If you have mutual activation, you would get phase separation with demixing. So this is a generalization of, if you want, motility-induced phase separation to 2 species. And again, when you add the population dynamics, it arrests, or it slows down at least, the growth, and you go from motility-induced phase separation to pattern formation. These are simulations of the PD we obtain, and I don't have dynamics for this one. With that, I'll conclude. I hope I've convinced you that a lot can be achieved using multi-continuity control to organize or to self-organize self-propelled particles. That's true in silico, but also in experiments, and also with synthetic active particles. And the theory starts to be well established, which is something nice because it gives us a lot of intuition about how we can guess what we should do to self-organize these particles. And I want to thank all my collaborators with whom I've worked on this for the past 10 years, and you for your attention.